So we are going to continue our discussions of acids and bases. All Bronsted acids produce H3O plus in water. We're going to say H3O plus, H plus, because we will use those somewhat interchangeably. If you add HCl and water together, that's a strong acid. It produces H3O plus and Cl minus. You can add that strong acid, and it's a limiting reactant, straightforward arrow only. You can add this weak acid, which is acetic acid, and water, and get an equilibrium process where you produce acetate and H3O plus. All acids produce H3O plus in water. Well, water itself does some dissociation and produces some small quantities of H plus and OH minus. We said acids produce H plus. Well, water itself produces H plus also. Bases, what we're going to talk about as bases, where there are other broader definitions of Lewis bases that we will talk about later, but bases that we will talk about all produce hydroxide in water. Lots of the bases that we will see are soluble things like sodium hydroxide, which, when you add water, breaks down into a sodium plus and a hydroxide minus. But neutral-containing nitrogen compounds are also bases. When you add them to water, this should say AQ. Well, that's a liquid, sorry. That's a weak base. It will accept an H. That neutral nitrogen will accept an H to become an NH plus compound, and hydroxide is produced. Well, on its own, water produces small quantities of hydroxide in solution. So water produces some hydroxide, some H plus, but it's neutral in general. Hydroxide dissociates a little bit on its own to produce a little bit H plus, a little bit H minus. Okay. Where am I going with this? If I write the Ka, the K expression for this equation, that would be H plus times OH minus divided by H2O. Well, we don't know necessarily, us don't know, but water, the concentration of water is considered a constant. It's a constant that's determined to be about 55 molar. We don't generally work with things that are that concentrated. Water, even if a little bit of it reacts, it's still going to be approximately 55 molar. Yeah, water is a constant. So because it's a constant, I can pull that water concentration over and multiply my Ka times water's concentration. So Ka times water concentration, that gives me this new constant called Kw. You just thought we've talked about a lot of Ks so far. We're not finished introducing you to new Ks. We've talked Kc, Kp, Ksp, Ka, and now Kw. That's still not all. Kw is the ionization constant of water. I can't come up with the other words. The ion product constant. I can't remember what you officially call that thing. But Kw is equal to H plus concentration times OH minus concentration. Hydronium is sometimes what you see written there instead, which is H3O plus, but we're going to do it H plus most often. Hydronium times hydroxide. H plus times OH minus. The ionization constant of water is 1 times 10 to the negative 14. So in neutral water, there are equal amounts of H plus and OH minus. So how much H plus and OH minus? If they're equal amounts, we can consider that an X squared kind of thing. X squared is equal to the ionization constant of water. Square root of that thing, you get 1 times 10 to the negative 7 molar. So in neutral water, the concentration of H plus is 1 times 10 to the negative 7 molar. The concentration of hydroxide is 1 times 10 to the negative 7 molar. This is the ionization constant at 25 Celsius. If you remember from our Le Chatelier discussion days, when you change the temperature, the K changes. So this really is only valid at 25 Celsius. Okay. So water is neutral. when your H plus and OH minus is equal. That's both equal to 10 to the negative 7. If you have more H plus than you have OH minus, that's considered an acidic solution. And on the other end of the spectrum, if you have more OH minus than you have H plus, that's considered a basic solution. However, because K values are constant, these things have to change in tandem, meaning if the H plus goes to a concentration of times 10 to the negative third, the OH minus shrinks to a 10 to the negative 11 concentration, because the sum of those has to be 10 to the negative 14, because that's our product constant up here. Same thing, if base is times 10 to the negative 5, OH minus is times 10 to the negative 5, H plus is times 10 to the negative 9. They have to change in tandem. When one gets greater, the other one has to get smaller so that it can still equal 1 times 10 to the negative 14 at 25 Celsius. Okay. It's true. The rest of the world does not like small numbers. 1 times 10 to the negative 7, 1 times 10 to the negative 3, 1 times 10 to the negative 11, 1 times 10 to the negative 5, 1 times 10 to the negative 9. The rest of the world doesn't like that. So instead of reporting these small numbers, we do a conversion, a mathematical operation, to convert this small number, tiny number, into a more reasonable numeric value. So what we do is take the negative log of that number, and in chemistry, when we talk about taking the negative log of a number, that's called a p. So if we take the negative log of 0.003, you can call that a p of 0.003. Negative log of that, punch it in the calculator, it becomes 2.5. 0.003 versus 2.5, the rest of the world likes 2.5 much better than a 0.003. Heaven forbid we call it 3 times 10 to the negative third. Oh my. If you do a p, aka a negative log, of 1 times 10 to the negative 7th, you get 7. So if I know that this is my H plus concentration, I can call this thing a pH. You've heard of that before. P of H plus concentration, the shortcut way to talk about that is pH. pH is 7 for a neutral solution. pH of this guy would be positive 3, because it's just the positive of my exponent when you negative log that thing. pH of this guy would be positive 9, because same reason, negative log of 10 to the negative 9th is positive 9. So pH 7 is neutral, pH 3 is acidic, pH 9 is basic. P means negative log, we just said that. There's lots of pH values, and there is no top or bottom. It's going to say that in a few clicks. There's no top or bottom to the pH scale. Most things have a pH between 0 and 14, but you can have a pH greater than 14. You can have negative pHs, absolutely. The cool thing about this little arrow diagram is it shows you, for those that don't love scientific notation so well, it shows you that really what I was just explaining, that 10 to the negative 11 is equal to a pH of 11, because we're doing log base 10 scale here. If I lost you, sorry. Yeah, we can talk about pOH, because pH and pOH have to change in tandem. H and OH have to change in tandem. If the pH of something is 7, it means the pOH is also 7, because, I didn't really plan to go here, but it's just coming out. We could do the pKW, that means negative log of 1 times 10 to the negative 14. That means pKW is 14. So pH plus pOH, I didn't really mean to write that in that order. pH plus pOH has to equal 14. That's because KW is equal to hydroxide times hydronium. I wrote it in a different order than I said it, but there it is. Okay, I really wasn't meaning to talk about it on this slide, but it came out anyway. We can talk about PCl, negative log of a Cl concentration. pKeq, we just call that a pK. We talk a lot about pKa. That's negative log of a Ka value. 12 molar HCl has a pH of, well, this is real easy. No rice tables necessary. 12 molar HCl means 12 molar H plus. So I negative log 12 molar because I negative log my H plus concentration. Negative log of 12 molar is negative 1.08. Yep. And this is where I was saying that, it says it on here, there's no top or bottom to the pH scale. True story. That negative 1.08, that's down there below 0. That's okay. It means it's really concentrated HCl. There's a lot of H plus ions floating in there. Okay. So we know to convert from an H plus concentration to a pH, we negative log. But what if you have a pH? How do you find H plus concentration? Well, if you have H plus, negative log the H plus, you get a pH. If you have a pH and you want an H plus, 10 to the negative pH. What do I mean by that? If I know that my H plus concentration is equal to 0.001, negative log of 0.001 gives me a pH which is equal to 3. If I'm given a pH equals 3 value, I 10 to the negative 3 to get my H plus concentration, which is 0.001. We will, molar, we love units, molar, we will go back and forth quite a lot with given the H plus, find the pH, given the pH, find the H plus. Okay. A sample of this solution of this acid was observed to have a pH of this. Calculate the value of Ka. Where do I start? Well, this is an acid. Is it a strong acid or a weak acid? Weak. It's a weak acid. How do I know it's a weak acid? Well, it's not on my list of 6 strongs that I have memorized. Are there more than 6 strong acids? Yes, but we've only had to memorize 6. And it's not one of my 6 that I've had to memorize, so if it's not there, assume it's weak. So typically we would do a little rice table, and we would say it starts out at 0.583 molar. None of this, none of that. We're going to lose some, we're going to gain some. Plus 6. And at equilibrium, what's my equilibrium concentration? Well, interesting. Calculate the value of Ka. So if I write a Ka expression, that's H plus times ASO3 minus over HASO3. So I could put in X times X over 0.583 minus X, but we're trying to find the Ka, not find X. So how do I do that? This is helpful. If the pH equals 4.63, I can actually find my H plus concentration knowing the pH. H plus equals 10 to the negative 4.63. 4.63, that's what that says. That gives me an H plus value of 2.34 times 10 to the negative 5 molar. Well, H plus concentration is equal to X. So I can actually put 2.34 times 10 to the negative 5 squared over 0.583 minus 2.34 times 10 to the negative 5. And if I do that calculation, I'm going to come up with Ka of this weak acid. This weak acid, do my calculation if I did it correctly. Here's what I got for my Ka. It's weak. That's a very small K value. It's a very weak acid. Got it? Good. How about some more? What's the pH of 0.2 molar HNO3? First question, HNO3, strong or weak? Strong. HNO3 is strong, and because it's strong, it means it produces all H plus in solution as a limiting reactant type problem. So 0.2 molar, yes, we usually put moles in limiting reactant tables, but if we assume a liter, 0.2 moles of this in the beginning, that says start, you're going to gain X amount. This is limiting reactant that I'm doing, and you have no reactant left over. No HNO3 because it's a strong acid. So the H plus concentration in a 0.2 molar strong acid is 0.2 molar. So pH is negative log of 0.2 molar. pH is equal to 0.699, 0.70, sure. It should be a very small value when you're talking about a strong acid. Strong acid pHs are way down low. This weak acid back here, that's still low because it's below 7, but it's not way down low because it's a weak acid. Okay, what about the pH of a 0.2 molar acetic acid solution? You knew that was acetic acid, right? Maybe. This one is different. Acetic acid, we write our equation. We're so good at writing equations now. Acetic acid breaks down into acetate and H+, and I should put my aqueous states on there. But because it's equilibrium, I do a little rice table. 0.200 plus x minus x squared over 0.2 minus x is equal to Ka. I cannot assume it's 0.2 molar H plus because it's a weak acid. So I can look up the Ka in a table. The Ka of acetic acid is 1.8 times 10 to the negative 5. I can do one more thing and assume x is small and get rid of that bottom x. Because the Ka is small, it's going to mean that x is small, and if x is small, you get to ignore the added subtracted one. So 1.8 times 10 to the negative 5 times 0.2, and then square root that. We get x equals, where are my notes? X equals 1.90 times 10 to the negative 3, and x is the concentration of H+. So pH is negative log of that thing. pH is equal to 2.72. Again, it should be acidic because it's an acid. It should definitely give you a pH below 7, but that strong acid, 0.7 pH, that's pretty low. This weak acid, same concentration, 2.72. Yep, a good way to check yourself. Let's squeeze another thing into this video. Weak bases. How do we talk about weak bases? We're going to talk about the structures of bases soon, but that's a compound that contains nitrogen that is neutral. And one of the things we're going to say about compounds that contain nitrogen that are neutral, those are in general good bases. So they can accept H's to become an NH2 and a plus and generate hydroxide in solution. Weak bases generate hydroxide in solution. Okay, how do we determine the pH of a solution that's, let's say, 0.2 molar? That dimethylamine is really the name of that thing, and you don't know that, and I'm sorry that I said it, but dimethylamine. If it's a 0.2 molar dimethylamine solution, what is the pH? It's weak, so we do a rice table. 0.2 molar. Ka and Kc, I should maybe say this, I don't really want to exactly, but Kc of this equation would be our products. That's CH3, I forgot the 2 up there. CH3 2, NH2 plus times OH minus divided by CH3 2 methylamine times water. What's the difference between Kc and Kb or Kc and Ka? Kc times water concentration, which we said at the beginning of this video is a constant, is equal to Ka/Kb. What's the difference in Ka and Kb? Kb is a weak base reacting with water. A Kb expression always has hydroxide as a numerator. Ka expression always has H plus as a numerator. Okay, that was a little bit of a tangent, but that's the difference between Ka and Kb, and that's the difference between Ka, Kb, and Kc. Oh, so many Ks. All right, starting over. We were supposed to be determining the concentration of this thing. So I'm going to write a Kb expression because I've got hydroxide as a product. It's Kb, not Ka. And I leave water out of my expression. That's really the reason that I went on that little tangent, to point out that my water concentration does not matter whatsoever, because the concentration of water is a constant. So when we're filling out a rice table, leave the concentration of water alone. I'm going to fix this. Make him green. Okay, so then I've got none of this, none of that, product. Going to lose some, going to gain some. And I set this equal to x squared over 0.2 minus x is equal to my Kb, 5.4 times 10 to the negative 4. I write real giant sometimes, which makes you have to squish things in other places. So I can solve for x, just like the very last example. Kb is small, therefore I can assume x is small, so I get to get rid of that one. So 5.4 times 10 to the negative 4 times 0.2. Square root that, whatever you found, and you get x equals 1.04 times 10 to the negative 2 is what I got. That's my hydroxide concentration, because that is x. So from here, need a little more space. From here, I know my hydroxide concentration. I can do one of two things. And you, as students, are likely to find a favorite and do it that way all the time. I switch back and forth. We know two things. Kw is equal to H plus times OH minus. We also know that pKw is equal to pH plus pOH. So I can do it this way. 1.0 times 10 to the negative 14 is equal to H plus times 1.04 times 10 to the negative 2. And I can solve and get my H plus concentration is 9.62, sure, times 10 to the negative 13. It should be a small number. I can negative log that number to get my pH, which is 12.02. If I was answering the question, what's the pH of a 0.2 molar dimethylamine solution, you could tell me it's 12.02 without doing what I'm about to do. I said there's two ways that students often look at this. One way, we're done. The other way, I can take that hydroxide ion concentration and find my pOH, so I negative log 1.04 times 10 to the negative 2. And I get a pOH. I don't know why I wrote that again. Let me stop that. I get a pOH that's equal to 1.98 plus pH equals 14. So 14 minus 1.98. pH equals, oh, great news. We got the same number. I don't care if you do it the purple way or the blue way. I will switch back and forth depending on the convenience of whatever I'm trying to find. Find the pH of a 0.2 molar dimethylamine solution. It's a base. It makes hydroxide in solution. You use a Kb value because it makes hydroxide. Then you can use your hydroxide to find pOH and then pH. Or you can use your hydroxide ion concentration to find your H plus concentration and then find pH from there. Either way, I don't care. This video has gotten lengthy. Ta-ta!